M23, I M23. I'm going to call J plus minus to be M12 minus plus I M13. And you can check that these behave just like the usual angular momentum raising and lowering operators. This behaves just like Jz. And I'm also going to introduce P plus minus. And this is P2 minus plus I P3. And then I will have P1 as well, just on its own. Okay. If I take J3 onto this state is just 0 because it's a scalar. It has no spin. Now let's look at a descendant. We could take P plus acting on 1/2 comma naught. So this is now a descendant state. If we act with D on P plus, well, P plus raises the dimension by 1. I told you it comes from this commutator over here. So, I mean, this is trivial, but let me just do 1. So from that first commutator, dP plus is P plus D on 1/2 on P plus D. dP plus is P plus D plus P. Good. Thank you. 1/2 naught. D on that is 1/2. So we'll get 1/2 plus 1, P plus 1/2 naught. And just as you saw, this commutator over here is responsible for raising the eigenvalue of D by 1. If you had n, you would get n plus 1/2 on P plus n 1/2 comma naught. If you had P minus, well, you can check that you would get exactly the same answer. So P plus, P minus, and P1 just keep raising the dimension by 1. If you take P plus on 1/2 comma naught and you act with J3, P plus raises the angular momentum by 1. And again, you get it just by applying the commutators, just like I did it here. You know the commutator between D and P. That allows you to calculate this relation. This one you will get by using the commutator between P and M. And what you will get is naught plus 1. P plus 1/2 naught. And if you had raised this to the power of n, well, that would have been an n. So every time we act with P plus, we increase the J3 quantum number. Every time we act with P minus, we decrease the J3 quantum number. So if we had acted with P minus to the power of n, we would have gotten a minus sitting over there. So basically, what I've, by the way, let me maybe just write down one more. If you have, we'll put it here, D on P, which one is it? 1 to the n, 1/2 naught will be equal to n plus 1/2, P1 to the n, 1/2 naught. That's how the dimension goes. And if you had J3 on P1 to the n, 1/2 naught, that remains 0. So P1 does not increase the J3 quantum number. So if you've got any particular descendant,
So J3 shouldn't be 0? J3 in this representation, because you don't have 0.
so J3 on this is 0, yes?
So why for P plus is not the same?
Oh, so when you come to P plus, so the field phi A is a scalar. The first descendant is a vector. Second descendant is a tensor, and so on. So this is a Lorentz scalar, but these are not. So that's why we're getting J3s.
What does negative eigenvalue mean there for J3?
Oh, so for example, if you go to spin 1, the L is equal to 1 multiplet would have J3 is equal to 1, J3 is equal to 0, J3 is equal to minus 1. Those would be the three states.
M, yes.
That's the M quantum.
That's the
Exactly.
M number.
This is the M quantum number. Exactly. Yep. So the P minus on the state, P plus on the state, and P1 on the state is exactly the three M quantum numbers of the L is equal to 1 multiplet. Yep. Good. Okay. So now we've got a pretty good idea about how D and J3 act. Yep.
Say that P plus acting on 1 half 0, that's essentially 1 half comma 1 or something.
It's 3 halves comma 1.
3 halves comma 1.
Yes, exactly. So now we know, in fact, how J3 and D act on any of our descendants, on the primary and any of the descendants. So now we can actually ask ourselves, what is the trace of a group element that involves only D and J3, and D and J3 commute? So the character that we're going to be interested in, I have to tell you what the group element is, and then we have to trace it. So the group element that we're interested in, G, will be e to the I, let's call it A. I'll write 2D. The reason why I'm taking 2D is that you can see that D's eigenvalues are always half integer. So it's like a half plus some integer. If I have 2D, then I've always got an integer coming out. So that's just purely for convenience. And let's say plus IB J3. Then I'm just going to change the notation just to make things slightly simpler for myself. I'm going to call this S to the 2D and T to the J3. So I've basically got S is e to the IA and T is e to the IB. No big deal. I've just relabeled things a little bit. And what should I do to get the trace of G? Well, the trace of G will be equal to, now I want to sum over all possible states in the multiplet, and A sits over there. So let's write down what the first few states would look like. Okay? So for the primary itself, okay, we've got the 1/2 comma 0, so we'll get a half for the D, 0 for the J. So the term corresponding to the primary will just be S. Plug in a half for D, so S to the 2D will just be S. Plug in 0 for J3, we'll just get a T. So this comes from this state. Plus. Now we'll get a state that looks like S cubed T. This comes from P plus acting on 1/2 comma 0. So let's see. If P plus acts, it's 1 plus a half. The dimension is 3 halves. 2 times 3 halves is that 3. And we said now J3 is going to be 1. So that'll just be T. Then there'll be a term which is just S cubed. Which descendant is this? P1, absolutely. So it's got to be 1P because you've got S cubed, so the dimension must be 3 over 2. And it's P1 because when I act with P1, I do not increase the value of J3. J3 is still 0. So put n is equal to 1 in this equation, n is equal to 1 in this equation. We'll get 3 halves, we'll get 0. Plug in the 3 halves for that eigenvalue, the 0 for that eigenvalue. That's the term that you get. Plus s cubed t to the minus 1. Which descendant is that? P minus. Perfect. P minus 1/2 naught. And so it continues. Okay? Now I'm going to write down the answer, and you'll see that it's got an incredibly intuitive form. The exact answer for this is s divided by 1 minus t s squared, 1 minus s squared, 1 minus s squared over t. So that's this character. Does anybody want to take a shot at telling me why the character looks like that? Why does the character look like that? If you've got 1 over 1 minus x, and you simply expand this thing, this is 1 plus x squared plus, and so it continues. This ts squared, that's got the quantum numbers of what? If you've got s squared, that's s to the 2d. If you've got s squared, what does d equal to? 1. If you've got t, you've got t to the j3. What's j3 equal to? 1. But the thing that increases the dimension by 1 and j3 by 1 is p plus. So this thing carries the quantum numbers of p plus. This thing is an s squared, so it's got d is equal to 1 and j3 is equal to 0. That's the quantum numbers of p1. This is the quantum numbers of p minus. So can you see, in the denominator, we've got 3 factors here. This is for the 3 momenta. And if you expand this out, you will generate the correct quantum numbers for all of the possible descendants when you act on the state. So this denominator over here is just keeping track of the different actions of the momentum. So the denominator is all about the descendants. The primary is what sits at the top. So you've really got a contribution from the primary over here, and in the denominator, you've got the contribution from the descendants. Now, we did this in 3 dimensions, but if you do it in more than 2, so for conformal symmetry, 2 dimensions and 1 dimension are special, 3 dimensions and higher are general. Here you had 3 factors because you've got 3 momenta in 3 dimensions with which you can produce descendants. If you're in 4 dimensions, you'd have 4 momenta, and there'd be 4 factors at the bottom. At the top, you'd again have the contribution from the primary. So this structure for the character is completely general. It really always looks like that. So, okay, let's write down a few characters then.
Just for knowledge, wonder, is it only for the conformal group that you have this structure, or you may have, for different groups you do have the same thing?
So I think this structure will come about whenever you have raising operators acting on a state, and those raising operators don't obey any additional constraints. If those raising operators obey additional constraints, you will have a numerator with pluses and minuses. And the first minus term tells you about the constraints the generators obey. The next term, which is a plus, tells you about the constraints that the constraints obey. The next term is a minus, which tells you the constraints abide by the constraints of the constraints, and it continues. But there is a structure that generalizes. This is just particularly free because the p's are free themselves. There's no constraints on them. Yeah. Oh, okay, good. Great. Thank you. Okay. So let's see. Is that good? There. Okay, good. So is that too high? Okay, good. Okay, so let's now write down what is chi 1/2 comma naught. This is s to the 2 delta. 2 times 1/2 is 2. And then we've got 1 minus t s squared, 1 minus s squared, 1 minus s squared over t. Okay? Oh, good. Sorry. 2 times 1/2 is 1. Good. That was a little test. Great. Just an s at the top. Perfect. Now, okay, guys, let's check. So we did so much work to get that character for the 1/2. Can someone tell me what this character is? S to the 2 delta, okay, 1 minus t s squared, 1 minus s squared, 1 minus s squared over t. Now, sorry? No, you see, the denominator is determined entirely by the p's, and the p's stay the same. Exactly, yeah, so the only thing that ever changes in these characters is the numerator. The denominator always stays exactly the same. Yep. Now, what about if I had spin j? Well, then the contribution from the primary actually has something in addition. You see, this would be a primary of dimension delta, so good. I'll have s to the 2 delta, but then I have a whole multiplet of spins. And in this situation, what would the character be? Well, the character chi j, this is now the SO3 character. This would just be the trace of t to the j3. And what values can j3 take if I'm in spin j? So my states look like jm, and m goes from minus j plus 1, j minus 1, and then j. If I plug all of those eigenvalues now into this trace, what do I end up getting? I just got t to the minus j plus t to the 1 minus j plus t to the j minus 1 plus t to the j. So that's just the form of the SO3 character. And all that I would do here is write chi j of t. And chi j of t is exactly that SO3 character. 1 minus t s squared, 1 minus s squared, 1 minus s squared over t. So that's the structure of the conformal characters. Now we've made a subtle error. This is nearly correct, but there's only one case, only one time when it's not correct, and we are so unlucky that's the one case that we need. When delta is equal to 1/2, there's an error. And let me show you what the error is. I want to study one of the states that we can have in our multiplet, one of the descendants. And the descendant I want to study is the following. Let's take Pj acting on 1/2 comma naught. And this is a descendant. What I would like to do, I want to act with a special conformal generator on this state. And let's just see what I get. Okay? So what will I get? Well, first of all, I can write pi a pj minus pj ki pj 1/2 comma naught plus pj ki pj minus pj ki. So I'm just doing the usual thing that you will do. I want to use the commutators. So this term over here with a minus exactly cancels this term over here with a plus. So I didn't do anything. And this term over here is 0 because you've got the superconformal generator, the special conformal generator acting on the primary, which is 0. So I've done nothing, I've just rewritten. Now, what is KIPJ? Well, we can look up at the conformal algebra. So KIPJ would be 2 MIJ minus 2 delta ij and d, acting on pj 1/2 comma naught. Then k acting there is 0, we'll get plus p, j. Then we've got a commutator ki comma pj, which is the same thing. Yeah. Okay, so now let's try to simplify this a little. So for the mij onto the p, I can write this as 2 mij pj minus pj mij onto the 1/2 naught. And this term is that term. And everything is good because you might think I've added something, but remember this is spin 0. So the m's kill the spin 0. So that extra piece that I've added, actually, that's nothing. That vanishes. Then I've got the d. So d acting on this will be 3/2 times by that 2. I've just got a minus 3. And delta ij onto the pj is pi 1/2 naught. mij onto that gives me 0. 2, the d is a half, so 2 times a half is 1, so I just get minus pi 1/2 comma naught. And now I can look at what's the commutator between mij, pij. And if you look at it there, I'll get a commutator, delta jj. Delta jj is 3 because we're working in 3 dimensions. So we'll get, this is 2 pi, we've got a 3 minus, and we'll have a delta ij onto pj. And delta ij onto pj is just pi. 1/2 comma naught. So I did nothing but use the commutator between mij and pj. I just have to set 2 indices equal to each other. And then minus 3 minus 1, this is minus 4 pi 1/2 comma naught. So let's see. Good. 3 minus 1 is 2, times 2 is 4, minus 4. That's naught. So we've got a descendant that's also primary. Is that okay? Well, let's calculate the norm of this state. So the state is pj 1/2 comma naught. If we dagger this, dagger. This will be 0, 1/2. And when we dagger the p's, we get k's. So if we say what is the norm of the state, let's call the state psi. Remember, the repeated index is always summed. We can ask what is the norm of psi, and that will be 1/2, 0, k. Let me use a different index. I'll say k, pj, pj, 1/2, 0. But we've just proved that k annihilates this state. So this is 0. So we have a null state. And if your state is normalized to square root of 2 or 10 or something like that, you can easily scale it and make it normalized to 1. But if your state is 0 norm, sorry, you can't rescale that to get something finite. So these states actually do not contribute to the trace, and you need to remove them.
Does this happen also in Euclidean, or it's a Lorentzian?
No. Okay. Let me explain to you when it happens. So the existence of this null state is actually not surprising. What are we learning? We're learning that pi 1/2, 0 is a null state. So how can we understand this null state? Well, the statement pi 1/2, 0 is equal to 0, this is the statement box phi is equal to 0. So in actual fact, the equations of motion for the free theory, because they're always just derivatives acting on a field, they always lead to null states. Our dimension of 1/2 was the free field theory dimension. So whenever your fields have dimensions in the free field theory, you always have null states. Okay? And by the way, so let's think about another primary operator that we know. Okay, and that's T mu nu, the stress energy tensor. You know that the stress energy tensor is conserved. Well, T mu nu is going to translate into a primary operator, and that primary operator will also have a null state. So whenever you've got conserved currents, there are null states. When you've got fields which are like the free field of the theory, there are null states. And those are the two situations in which you get null states. Okay? So let's now write. Sorry?
Statements, and only statements. You get a null state if and only if you have a free field or a conserved current.
Yes. Good. But okay, so and basically, this is the other way to see it. So this is an exercise that I've given you in the tutorial. What you could do is, so here we calculated this k acting on the state with dimension 1/2. But you might choose to do it with any dimension. And then you can check for what values do you get 0. And you can calculate this norm for any dimension. You find if delta is greater than 1/2, this norm is positive. If delta is equal to 1/2, this norm is 0. And if delta is less than 1/2, this norm is negative. And that tells you there's no unitary representation of the conformal group with that dimension. So there's actually lower bounds for dimensions. And if you saturate them, you get null states. If you go beyond that point, you don't have a unitary theory. Okay, good. So now let's fix our top formula for chi 1/2 naught. Okay? Let's see how to fix that. This over here, this is a primary operator, a primary state. It has dimension delta equal to 1, 2.5, 2.5. That's 5/2. This is contracted PJ, so there's no spin, and there's no spin there. So again, the spin is 0. And what happens is this state and all of its descendants are null, so they must be subtracted. So to perform that subtraction, we say minus s to the 5, because that's 2 times the dimension, and the spin is 0, so we can just leave it like that. So that's what that character, so that character now is correct. This character is correct for delta greater than 1/2. And now you can also get a problem with these representations, and let me tell you when you get the short representation. If you have spin j, then there's also a bound on the dimension. Delta has to be greater than or equal to j plus 1. And when delta is equal to j plus 1, you get null states. So let me tell you what the character is in that case. So if we've got dimension of j plus 1 and spin j, what you would naively write down is s to the 2 times the dimension, 2j plus 2. You would put the SO3 character, so chi j of t, and you would put your descendants. So that's what you thought the character would be. Now, what this corresponds to, this spin j guy, this corresponds to a tensor that has got mu1, mu2, going all the way up to mu j. And the null state is the statement that this is conserved. So we need to subtract off everything from that guy who's null. What does this guy look like? This has got dimension j plus 1. This has got dimension 1. And the spin, there's now j minus 1 indices. One index has been contracted. So the spin is j minus 1. And now we use our usual formula. We say s to the 2 times the dimension, 2j plus 4. And we'll have k to the j minus 1 of t. So that's the complete set of characters for the C of t. Okay. Would it be helpful for anyone to ask a question now? If anybody would like me to.
So T mu nu has 2 indices, the spin 2.
Spin 2, exactly.
And dimension 2 also.
And, let's see. Dimension, yes, 2. Yeah.
So T mu nu is one of these j's.
Yes, exactly. T mu nu is one of the j's. It's the s is equal to 2j. Yep. Yeah. Okay. So now I'm going to tell you what our character formula is. And you can go away and check in Mathematica that this really is true. So which characters are normal? Let's say which characters are normal and which ones are special, the short ones. So this is special. Unusual. This is usual. This is usual. And this is special. Generic, non-generic. The only characters that we are going to use are the non-generics. Okay, they're the only ones that appear at this level. Because we deal with the free field theory and because we are considering products of 2 fields. If you have 3 fields or more, in fact, then everything is generic. Yep. So it's bilocal and free. That's what's special. These all correspond to conserved currents. What are conserved currents dual to? Gauge fields. So we're dealing with a theory with a lot of gauge symmetry. So let's write down what the answer is. Good. So chi 0, 1/2.
So just a question. So you say that the formal symmetry, especially in 1 and 2 dimensions, 3 and above, it's kind of
3 and above, it's kind of standard, yeah.
characters. If I name in 4 dimensions or 5 dimensions, there will be something similar.
Exactly the same.
Have 0, which is special. It's something else. It's like
Exactly. Yep. Yep. So chi 0, 1/2 squared, well, you'll get one field which is dimension 1 and spin 0. That's just phi dot phi at the same point. And then you have plus, and now here you have, well, okay, I can write it actually as a plus. These are characters. Plus, we can have a sum from j is equal to 1 to infinity chi j plus 1 comma j. So that tells us all of the fields that appear. Yep?
Should it be a half comma 0?
No. Okay, so let's take a look. So phi a was 1/2 comma 0. What we've done now is we've taken a phi a times a phi a. That's why we've got the chi 0, 1/2 times the chi 0, 1/2 squared. Oh, is that what you were asking about? Sorry. Yes. 1/2 0. Good. Thank you. That was another test. Okay. Great. Now, yep.
The usual one, the third character.
Yep.
Is for any delta, which is not j plus 1.
Delta must again be greater than j plus 1. Yep. So there's always a lower bound. Yep. Okay. Now, so I hate to do this to you, but I'm going to do it anyway. That formula is not quite correct. And why is it not quite correct? We made one little error. When we think about our bilocal, the phi a, that bilocal is contractions of two bosons. So you can swap the two bosons and that's a symmetry. We didn't put that in anywhere. This answer is exactly the correct answer if your bilocal had been a complex field. And if you look at the spin 1, for example, let me give you an example of what the spin 1 current is, because I think you know this. When j is equal to 1, the current is this. It's phi a star d mu phi a minus phi a d mu phi a star. And you can see we said this was dimension 1/2, this was dimension 1/2, and this was dimension 1. 1 plus a half is 2. So j would be 1, and the dimension would be 2. So this is the j is equal to 1 term in the sum. But you can see that if I set phi is equal to phi star, this just vanishes. Okay? All of the odd ones disappear if you set phi is equal to phi star. So, in fact, if you had taken into account this fact that it's symmetric, you can do that. There's a systematic way to do that, but I'm not going to describe that. What you will learn is you keep all of the even spins. So you would get 2j plus 1 and 2j. And now that formula is correct for our theory. Those really are the representations that appear. So we can start.
Like I take the formula on the left and I just check it.
Yes, exactly. Plug it into Mathematica. Yep. But so.
It's not self-obvious, no?
Sorry?
It's not self-obvious, this formula. Just I take these things, I put them there and I have them up.
Okay. There are cleverer ways to do it that I'm not going through. Yeah. So there is a systematic way to do it, but you could check this now. You know enough to check it. Yep. Okay. So why is this important for us? Well, this term over here This corresponds to a bulk scalar. This is in AdS4. So that primary in the CFT, in the 5-5, will correspond to a bulk scalar in the AdS4. From here, these are all conserved currents. All of them. And conserved currents correspond to gauge fields. So we have gauge fields of spin 2, 4, 6, 8, and continuing. Because there's a gauge field of spin 2, we have a graviton. Because there's a graviton, this is a theory of quantum gravity. Okay?
So these currents, they are bilinear in the field phi?
They're bilinear in the field phi, absolutely. So let me tell you what I would like to do now, and then we'll take a little break.
So,
Yep.
so then when you are looking at your CFT and you find the first primary, and then you find other states that are also look like primaries, you have to make sure that they are not conserved currents or check if they are.
Exactly. So whenever you find a state that's a primary, check that it's not a conserved current and it's not a free field. You absolutely have to check that. These bounds, by the way, are known for CFTs. You can go and look them up. Yes?
So the spin 2 will be the graviton, and is there any interpretation for the spin 4, 6, and so on?
They are higher spin gauge fields. They modify the theory. So this does not look like Einstein gravity. It's some modification of it. And nobody's found a way yet to break. This theory has an enormous gauge symmetry. Nobody's found a way yet to break that gauge symmetry, so you are just left with Einstein. If you could somehow break it and make all of the other gauge fields heavy and leave only the spin 2, I think this would become physically much more interesting. But the point is there's no supersymmetry and it's not a string theory. So I think that anything that you learn from here, you can really claim I'm learning something about holography and how holography works. When
Actually, you cannot even write a Lagrangian for this guy, no?
For the higher spin guy?
Yeah.
Absolutely. So on the higher spin side, the best that's done is classical equations of motion have been written. The Vasiliev equations, right. So you can write Vasiliev equations of motion. The point about the Vasiliev equations of motion is that they go to all orders. They're all orders in the interaction. It's an exact set of classical equations. Then you could say, let me try to quantize this theory. To quantize the theory, you need to find an action that that equation of motion comes from. And we are almost 30 years now since we knew the equation, and nobody wrote down a good action. So it looks very hard to do. And without an action, you can't start a path integral quantization or anything like that. So there's a lot that's not known about this higher spin gravity, but there is stuff that is known. Okay, now let me tell you what I want to do next. So on the CFT side, what do we have? We've got a bulk scalar. We've got a scalar. This is on the CFT side. Let me call this phi. And we've got a whole bunch of conserved currents. Let me call it mu1 up to mu2s. These are symmetric. They're traceless. They're conserved. So I can count how many independent degrees of freedom there are inside J. And for phi, it's easy. It's just one. On the gravity side, I have a bulk scalar. Let's make it capital phi. And then I have these gauge fields. So I'm going to call this A, and I'm going to put index M1, M2, up to M2S. And what I can do is, now this is a gauge field. So if I want to figure out what are the independent degrees of freedom, I can fix the gauge. I can solve the gauge constraint. I can take into account that this guy is traceless, this guy is symmetric, and I can count how many independent degrees of freedom. And what I will find is the independent degrees of freedom in the CFT exactly matches the number of independent and physical degrees of freedom in the gravity. And they do it spin for spin. And then I can ask myself, can I actually build a mapping which will take me from the CFT degrees of freedom to the gravity degrees of freedom. Can I correctly map these 2 degrees of freedom and then check it? That's what I'm going to describe to you in the next lecture, and that's sort of our approach towards trying to prove this holographic duality between this very simple CFT and the higher spin gravity. So I think this is a good place to refuel with coffee. Yeah.
Thank you very much, Robert. If you have questions, yeah.
Why doesn't this character expansion work for example, delta less than J?
So, okay. So, in fact, the character expansion would work for deltas less than J. What happens, though, is the representation is not unitary. Yeah. So usually, so the restrictions that I put down are because we want to restrict to unitary CFTs. There's a lot of interesting work happening on non-unitary CFTs, so they appear to be relevant. I think even some condensed matter literature uses non-unitary CFTs. So not obvious that nature only uses unitary CFTs, but that's an assumption that I've been making.